Good morning and most welcome to 1191 of Quantum Mechanics for Laymen. We venture now into Chris Fields, the American quantum physicist with very very conservative attitude to the orthodox quantum interpretation. And he says, as a little summary from last lecture, that one thing forgotten is the clock. It seems in the quantum experiment to reside outside the measurement and thereby not being taken as part of the experiment, seen as a permanent time. By permanent time, I don't mean it is constantly showing the same time, 10:15. No, not at all. Permanent time means it is continuous. It is the same time, identical time, so to speak. So one moment is the same flow of time, so to speak. This is an assumption. Chris Fields, and it makes a whole change. In a way, it resolves what is usually called entanglement, not to become as mysterious, actually quite normal. Let me go to the summary of the last paper I started with, Unitary Quantum Theory as a formal framework for a theory of consciousness. Summary: the quantum world. The quantum theoretic picture of the world briefly outlined here is, as noted earlier, utterly unlike the essentially Aristotelian picture of the world that we developed by observing and manipulating objects as infants and young children. Indeed, it's difficult to imagine a picture of the physical world that is less like our intuitive picture than is the quantum world. Some 600 years of increasingly precise experiments tell us, however, that while our intuitive picture of the physical world is accurate enough for hunting, agriculture, social life, and even substantial feats of architecture, it fails utterly when pushed into new domains. The mechanical devices ushered into human culture by the Industrial Revolution required the classical physics of Galileo and Newton, as radical in its day as quantum theory is now. For their comprehension, the electronic devices of the mid to late 20th century require quantum theory for their comprehension. Every time we send an email or take a digital photograph, we affirm, Bohr's quip notwithstanding, that the world we live in is a quantum world. It is time that we understood this world on its own terms. The fundamental concept that quantum theory introduces is entanglement. The quantum world is an entangled world. It is not separable into bounded, time-persistent, re-identifiable entities that can be understood. Ceteris paribus, independently of one another. Our idea of independent bounded systems that persist through time is, from a physical point of view, strictly an approximation. It is often a good approximation, quite good enough to enable experiments that employ bounded apparatus that can be re-identified easily from day to day in the laboratory. Experiments that have uncertainties better than 1 part in a billion. What this means, however, is that it is a good approximation for us. We define the systems that we consider to be bounded in space and time. And these are the systems for which approximation is good. How does this work? What enables us to define systems that appear to us to be bounded? Understanding how this works requires understanding how observers interact with the systems that they have defined. This in turn requires understanding what observation and observers are. This question of what counts physically as an observation or an observer is almost always avoided. Zurek, for example, explicitly places this question outside of science, stating that the observer's mind that verifies, finds out, etc., constitutes a primitive notion which is prior to that of scientific reality. Fuchs asks somewhat more pointedly, would one ever imagine that the notion of an agent, the user of a theory, could be derived out of its conceptual apparatus? Stapp follows von Neumann in treating observers as amalgams of physical and psychical components, with the latter inexplicable in physical terms. Hameroff and Penrose developed a theory of observation centered on neuronal microtubules localized within the brains of the observers, but offer no physical account on why these particular macroscopic structures and not others should be privileged bearers of quantum coherence in an otherwise classical world. Most physicists avoid the question altogether, remaining content to regard an observer as just another quantum system. This is the view of Schlosshauer, or even a la Einstein as a moving coordinate system. This is how Rovelli sees it. And an observation as any event that transfers classical information to an observer. It is my contention that understanding the quantum world requires understanding observation as a physical process, and hence understanding how semantics are overlaid on dynamics. From a quantum theoretical perspective, this is the question of how observer-system entanglement implements a mathematical operator, a von Neumann projection, or in more modern terms, a positive operated value measured, a POVM, representing a quantum theoretic observable. From an information theoretic perspective, it is the question of how classical symbol-based information processing, classical computation, can be implemented by unitary dynamics. The latter question is central to process to be interpreted as a quantum computation. In particular, a quantum computation that accepts a classical question as input. This is very important. So the input can be classical. And this is called a POVM. And this is representing a quantum theoretic observable. So from an information theoretic perspective, it is the question of how classical physics, symbol-based information processing, classical computation can be implemented by unitary dynamics. And that is a quantum computation that accepts a classical question as input and yields a classical answer as output. A number of formal answers to this question now exists in the form of well-defined semantics for quantum programming languages. These formal answers, however, assume an observer. The challenge is to replace this assumed observer with a physical model of observation. The next section further characterizes this challenge and outlines a solution. So, to be a very short summary here, it's the boundaries that creates the observers. And the boundaries are flexible. We are simply not aware of their flexibility because we just assume as observers. And it's interesting that he puts everyone into the same box. Penrose, Hameroff, Rovell even, and slightly fascinated also Henry Stapp goes into that box. So, but think of the whole system and divide a part of that system and call that division, that piece of the cake, the observer, and the rest is thereby the observed. Boundaries implement observers. Treating an observer as simply a quantum system with associated coordinates unfortunately provides no insight into how an observer accomplishes the two key tasks that compose observation. First, the acquisition of classical information and its storage in a stable long-term memory. It is successful execution of the second of these tasks that renders an observation reportable and hence usable by either the original or some other observer as a basis for comparison with future observations. As noted earlier in the special case of systems employed as clocks, this ability to compare current and previous observations is essential to the definitions of both measured time as opposed to symmetric time and this is what I was pointing to in the beginning, time persistent individuality. Zurek, 2003, takes this memory encoding and reassessing ability as criterial, remarking that what distinguishes observers from mere apparatus is the ability of the former to readily consult the content of the memory. The common picture of an observer as a system or even as a conscious agent that deploys a measurement operator to interact with the quantum system is therefore incomplete. Any observer capable of reporting comparative observations must deploy two measurements operators. That acquire classical information from two separate quantum systems. The system of interest and the observer's own physically implemented memory. These two systems must be separate, not entangled, if the memory of a previous event is to be independent of the event currently being observed. Again, as noted earlier, such separability is always an assumption and always an approximation. It is relatively straightforward to arrange circumstances in which this separability fails, sometimes spectacularly, as in the case of human memory. For instance, change blindness paradigms, Simons and Levin for a striking example, and that example is very striking. I think we are completely unaware of that. I would try to put a link to the Simon and Levin's experiment. How can this assumption-laden semi-classical view of observation be reformulated in a way that makes it fully consistent with quantum theory? The two components of the standard view clearly must be dropped. The idea that observer, observed, and memory are separable, and the idea that current and previous memory contents can be compared side by side. It should be emphasized that these ideas are not incidental, but rather are central to the traditional conception of observation, and indeed experimental science. David Bohm, one of the foremost advocates of holism in physics, still insisted that the very idea of making an observation implies that what is observed is totally distinct from the person observing it. The ability to compare current and previous observations side by side with a non-problematic presumption of independence is essential to the notion of experimental replication. These ideas are, however, inconsistent with unitary quantum theory and must be rejected or treated as, for all practical purposes, approximations. If unitary quantum theory is to be taken seriously as a correct description of the world. So the inseparability of the observer from what is observed, and we venture into memory. And Bohm pointed out this fallacy of thinking the observer to be wholly separate. Quantum theory replaces the classical idea that observer and observed are separate with its opposite, the idea that they are entangled. What entanglement does in this, or in any case, there was a very complicated case here. I will try to get more into it to understand it, and I will do in 2 lectures, hopefully before Wednesday, a little short take on it. What entanglement does in this case, or any case is classically correlate conditional information. The classical correlation only appears if a particular measurement is made. But if the measurement is made, the correlation is exact. Hence, quantum theory replaces the traditional notion of absolute, objective, classical correlation with the notion of conditional, classical correlation. It also replaces the idea that classical correlation can be viewed as classical information transfer from the observed system to the observer with the notion of correlation full stop. This is very important. Entanglement is not a classical causal process. Observer and observed are equally entangled both before and after the observer records the measured outcome value. So, according to Chris Fields, entanglement is projection of classical quantum mechanics into the classical world, and all of a sudden, whoops, we get entanglement, mysterious, spooky action at a distance. Well, I have a hunch here already. Of course, it's not precise, and it's bound not to cover anything, but, well, not much. The above discussion treats the observer and the observed as monogamously entangled. That is, entangled with each other and with nothing else. It is only under this condition that classical correlation can be exact. Monogamous entanglement, however, requires isolation. In particular, it requires isolation from any surrounding environment. Any physically efficacious isolation, however, violates decompositional equivalence. No system is actually isolated. So what can it mean to say that entanglement provides a mechanism that correlates an observer with an observed system? As shown in detail by Zanardi, 2001, where the two components of an entangled state are monogamously entangled or measurably entangled at all, is not an objective fact, but rather dependent on both the chosen TPS, the availability of resources, such as time or energy, that enable particular measurements with respect to that TPS. These dependencies can be combined into the single notion of quantum reference frame, a bounded quantum. and hence physical, system that two observers must jointly access in order to exchange classical information and hence to communicate observational outcomes. Because a quantum reference frame is not an abstraction, this is very, very pertinent, but a physical system. So the reference frame is physicality itself. It's not a frame in physicality. It is not a drawing up on things that are projected to physicality. It is physicality itself. So press it a bit to that direction, getting rid of an idea of lines being out there, which I can promise you is very hard. We do have the Cartesian coordinate system in our blood. Because a quantum reference frame is not an abstraction, but a physical system, accessing it requires observation. Hence, what observers can be thought of as sharing is an observable, a POVM. An observer in this context is moreover any physical system that is classically correlated with and hence shares classical information with another system. The idea that entanglement creates a classical correlation between an observer and a system being observed depends therefore on the assumption that observer and observed share POVM. As noted above, in the case of systems defined to be clocks, however, such an assumption is always a piece of semantics. It is a specific carving up and naming of the world that is taken to be privileged. It is nothing, it's not something that the physics of the situation provides. It is not a given one. It is not a gift from nature, the boundaries, and so we usually assume boundaries in reality between observer and observed. This is being put into question here. It is shown to be not clear what that would mean even. What we have is the totality of the totality. Everything is included. Time should be not outside of the measurement, like in a clock. It is constantly part of what is happening. The boundaries we make up, look at this one, that boundary does not come from physics itself. We make that to create materiality, objects, and so on. But somewhere in the process we have become unaware of that. We were made aware of that in the event of quantum mechanics, starting from the 1920s. Observer, and here we have the observed. That border being moved in that direction or in that direction. There is a movement in physics. I can put in some examples by myself here. Thermodynamics and hydrodynamics move this. I would say thermodynamics moves it in this direction of the observed, and thermodynamics keeps it a little bit closer to this line, but it's still on the right side here. That movement makes thermodynamics and hydrodynamics to be incompatible with each other, but also incompatible with Newtonian physics. So this is already a fact, as pointed out by philosophers of science. Not understood by Thomas Kuhn. Paul Feyerabend had this maybe as one of his three main objects to show that it's movable, need to be movable. Well, we do move it anyway. Quantum mechanics says understanding that we move this is an essential part of an experiment. Otherwise, we cannot make accurate, concise predictions. Remember the Alice and Bob example. We had that in the beginning of the course in quantum mechanics for laymen, and it needs to be repeated. It's very important in this context. What is problematic for us is that it gives different results in some cases, so that Alice do not see the same turnover of the coin toss as Bob. This is predicted by quantum mechanics, and it's not a problem. This is actually what quantum mechanics does. The resource that quantum theory provides for establishing classical correlations and hence classical information sharing between systems, the resource of entanglement, thus comes with important strings attached. Entanglement only provides for the sharing of conditional classical information of the form, if classical information is recorded, it will be correlated across systems. Entanglement provides even this conditional sharing, moreover, only in the context of an assumed quantum reference frame, or a POVM. This latter assumption is a semantic assumption that any two parties sharing classical information must make about each other. The conditionality and contextuality that quantum theory imposes on classical information, and hence on the concept of observation, makes these a far cry from the traditional usages in classical physics, in which information was assumed to be objectively available for the taking in the environment. You hear the difference here? Just for the taking, just for the grabs. They are not, however, surprising when viewed from the perspective of 20th century systems theory, philosophy of language, or even perceptual psychology. Do I dare to put Gibson in parentheses? The lesson of the 20th century in all of these domains is that shared meaning is an assumption one that can easily turn out to be wrong. Abandoning the still classical assumptions about observation embedded in standard interpretations of quantum theory for a bare account in terms of entanglement and quantum reference frames catches the physics of measurement up to the realizations made by logicians. Tarski, Turing, Ashby-Moore, Quine, Wettstein, and cognitive scientist Newell about the relationship between semantics and its physical encodings. Toward a quantum theory of reportable experience, well, this is what it is all about. All reportable contents of experience, all sensory perceptions, memories, imaginations, emotional feelings, and epistemic, aesthetic, or moral feelings are remembered and reported as classical information. The theory sketched above therefore applies to any physical encodings of such reportable experiential contents, including not just encodings in artificial media, but also encodings produced by voices or bodily motions, or encodings in biological media such as electrochemical activity patterns in brains. Taking quantum theory seriously as a correct description of the physical world involves taking seriously what it has to say about the origins and dynamics of such encodings. Quantum theory first specifies the conditions under which encodings of reportable experiences are generated. Reportable experiences are encoded whenever a spatially bounded collection of physical degrees of freedom composing an observer is entangled with a spatially bounded collection of degrees of freedom composing an observed system. It further specifies that while such entanglement characterizes all spatially bounded collections of degrees of freedom at all times, it does not have an objective description. How a system is entangled with its environment, and hence what classical information it encodes as reportable experiences, is dependent on quantum reference frame from which system-environment interaction is viewed. Such reference frames are not unique. Hence, as Dugic and Jenknich-Dugic 2012 put it, the emergent classical world is not unique. Indeed, every observer can be regarded as recording a different emergent world. The common assumption that what other observers experience can be assumed to be like what we experience. There is therefore in general mistaken. The experience world of the vast majority of other observers can, instead be safely assumed to be nothing like the world as we experience it. The vast majority of other observers may, for example, experience nothing like what we call space or time. Quantum theory also specifies how the classical information encoding reportable experiences is encoded. It is encoded on the observer-environment boundary. Different ways of drawing the observer-environment boundary correspond to different quantum reference frames and hence to different encoded experiential contents. How these reference frames are chosen or boundaries are drawn, however, can have no physical consequences. Hence, what contents are encoded can have no physical consequences, which is in itself very odd. These classical encodings that render experiences reportable are, therefore, physical phenomena, but not causal phenomena. Their lack of causality, either within or outside of the boundary defining an observer, as I mentioned earlier here, there is a boundary established. And this is this boundary Chris fields are pointing to. How these reference frames are chosen or boundaries are drawn, however, can have no physical consequences. Hence, what contents are encoded can have no physical consequences, but can have, the classical encodings, no, I was correct, that renders experience reportable are, therefore, physical phenomena, but not causal phenomena. And in quantum mechanics, we are above all interested in the causal phenomena. That is what holds the semantic. I put a pause here and get change of environment here. So we changed the environment here. Let me continue with the paper. So we're on page 11 here. There will be linked so you can download the article and follow while I read, so to speak. Let's see if I can get some better sound quality. Yeah, repeat the last one because this is incredibly informational, condensed. And when I say I will attach it, I would say it's so condensed it almost defies reading. But reading it aloud helps. But it's not a text when sit down in the sofa and understand. Quantum theory also specifies how the classical information encoding reportable experiences is encoded. It is encoded in the observer-environment boundary. Different ways of drawing the observer-environment boundary correspond to different quantum reference frames and hence to different encoded experiential contents. And this is very important. Where the line is drawn, what is the content of the observer, whatever that might be. It could be anything. How these reference frames, remember what we had on the whiteboard before, are chosen or boundaries are drawn, however, can have no physical consequences. Hence, what contents are encoded can have no physical consequences. The classical encodings that render experience reportable are therefore physical phenomena but not causal phenomena. The lack of causality either within or outside of the boundary defining the observer is assured by the quantum theoretic prohibition of local determinism. Indeed, the Conway-Cohen theorem assures that such encodings are not even stochastically deterministic. That is, not even statistic can come in and make it semi-deterministic. The picture that emerges when the implications of quantum theory for encodings of experience are taken seriously is thus both expansive and bracingly counterintuitive. Quantum theory makes observers ubiquitous in all locations and at all scales. It allows all interactions between spatially bounded systems to be considered observations. As Fuchs puts it, quoting William James, an entangled universe consists of an all-pervasive pure experience. This pure experience of entanglement is encoded as reportable classical information at all boundaries, but from the perspective of the physical dynamics, they are all both arbitrary and notional. Hence, all reportable experience, from a fleeting sensory impression of redness to the memory of an experience past, to the most startling and profound insights, are from this perspective created equal. All are encodings on boundaries drawn between degrees of freedom that are not, in fact, separable. Such boundaries are, moreover, only drawable with respect to a quantum reference frame, the choice of which is always pragmatic and never objectively determined. The intimate relationship between reportable experience and choice of quantum reference frame suggests that experimental approaches that characterize the implementation of reportable experience in human beings or other animals also implicitly characterize quantum reference frames. If this is the case, suitable experimental manipulations would be expected to reveal measurable quantum effects at all biologically relevant scales, from biochemical and macromolecular processes in neurons to cognitive processes in individuals or groups. The growing evidence for quantum effects in human categorization and conceptual reasoning suggests, from this perspective, that activation processes in large-scale neural networks will soon be found to exhibit measurable quantum effects as well. Conclusion. Quantum theory has traditionally been regarded as unsatisfactory as an explanation on what is going on in the physical world. It has therefore been supplemented with a wide variety of interpretive assumptions, all of which introduce aspects of classicality and hence reduce the quantumness of the theory. While such interpretive assumptions bring the theory closer to the familiar realm of human experience, they render its explanations circular and systematically hide what quantum theory is attempting to tell us about our world. When quantum theory is stripped of interpretive assumptions, it tells us two things of great significance. First, it tells us that semantic is not given by dynamics. Very good. Semantics is instead given by boundaries, and boundaries have no physical consequences. Aspects of the world that have no physical consequences are often thought of as epiphenomena. Boundaries are not epiphenomena. Indeed, boundaries are not even phenomena. Boundaries enable phenomena by creating and encoding classical information. The arbitrariness and ephemerality of boundaries renders phenomena arbitrary and ephemeral. Selecting a different boundary yields a different set of phenomena, one that may be utterly different from the original. Moreover, any boundary may be selected and yield a semantics and a set of phenomena as a result. The second lesson of quantum theory is that our position as experiences are not privileged. We are experiences, but so are all other systems, seen and unseen, that surrounds us. We're not even particular complex experiences. Huge numbers of distinct systems contain each one of us, and in huge numbers more contain all of us. Moreover, none of our experiences are privileged with respect to any others. All reportable, and this is incredibly crucial, all reportable experiences are equally encodings on ephemeral, consequence-free boundaries, traversing entangled states. The challenge for an emergent science of consciousness is to develop experimental techniques that reveal how entanglement between definable collections of degrees of freedom produces experiences encoded on the boundaries that we call human beings. So physicality is caused by a specific boundary, and those frontiers can be drawn differently. The point that Chris Fields makes is that we are simply not aware that we are able to draw the boundaries differently. And by not knowing that, not having that knowledge, we are making ephemeral, random objects. They don't last. Observations that are at the very best passing. And also the subject itself will be passing. Randomness has entered the picture. We don't build up stable, organized, single attractor driven systems that can be permanent over time or more permanent. We make do with impermanence. We make impermanence our bread and butter, or the lack of the same. We are like seashells without shells. We don't have the security. We cannot have it, because by not understanding this, we make each and every experience wholly subjective, emotionally laden, and not very useful. And Chris Fields is trying to take up the message of quantum mechanics to our benefit, because it points to a fact in our lives that making boundaries unassumingly and without decision and want and wishes, where there is in time. We started with the clock, an understanding of the clock as being outside of the system will draw in randomness into the observation or observer, both of them. One is not cut off from the other one. They are part and parcel of the whole thing. And only by understanding that, we can come with an outcome that is either, if we want classical to be more correct, or quantum if we want to do that. He pointed to the POVM, and that's a thing that makes predictions wholly classical as long as you understand the boundaries. That's very important. Without the boundaries, it can be made hopefully stochastically deterministic, but maybe not even that, as in the last example. So this is a pointing to a greater understanding as well, because those boundaries, if they're not known, they're bound to turn up, very good pun, sorry, everywhere, in our thinking, in our doings, in our bodily doings, our actions. They're bound to cause a lot of problem because it's a lack of knowledge. It is similar, but much worse than not knowing the boundaries of one's own house, not knowing where it ends. And then you will bump into walls, ceilings, and floors and doors. And this is happening now. I taken up that earlier when we spoke of Bujaki. Jirji Bujaki shows that modern people cannot orient themselves. The director cells cannot be activated with the coordinate systems that is outside of us. This has been vehemently proven by fMRI scans. And without localization, that can only start with our cells, which is also a boundary that needs to be made to be able to localize oneself. there cannot be a healthy individual. So we collapse in sofas, in beds. Bujaki said that is the torturing the bodily system. And we get used to the torture, and then probably we might call that classical physics or the modern day of life. And there are even people who think it's comfortable to collapse in a sofa. That's the most torturous thing you can even imagine. They point to other people, everyone is doing it. It's like they don't not having a body of themselves. Well, that's another chapter, and this is what Imi Kilkres calls modern day schizophrenia, where our own selves are so distant from us because of the unknown boundaries that we no longer care about ourselves. Well, if the news of Chris Fields is coming out, and I think they are bound to, it's very hard to argue against his findings. What you can do is not understand it, and that's easily done, but that's a whole other ballpark. It was very nice having you today. I think I should say, well, still good morning. Bye bye for now.